In my previous video, I clicked the wrong button and messed up. So now I have to redo this part. Okay, continuing, here's the negative sign. I wrote it out, and that's how it makes sense. So next, continuing on section 6.4, on page 29, let's look at the inverse of a transformation. Now, a set of equations where you have f(g(h) and it's transforming something from xyz space to u(v)w space, we can consider that as a kind of a transformation where each point xyz got tossed into some other point as u(v)w. Now, sometimes it's possible to solve for xyz in terms of u(v)w. In other words, we yank it out and pull out the inverse function. And if that is the case, then we have the inverse, okay, where it takes stuff from u(v)w and toss it back into the xyz space. And then, so that would be called the inverse transformation of the original transformation. Now, currently, we only care about the implicit differentiation and not care too much about what transformation does. So the only thing we are focusing right now is trying to figure out how do we do all the derivatives, okay, if the inverse exists. So we don't, in other words, we don't have to know what the inverse function is, or even if it's possible for us to even pull it out, that is explicitly. Okay, we know it can be done sometimes, but we might not know, we might not have an equation for it. However, even then, we can calculate the partial derivatives with the trick that we've been using so far. Now let's look at page 30, okay? There is we have a bunch of functions, right? And then we're gonna write it like, let's look at this. Now we have the big F, which equals to u minus small f, and we're going to be setting these things to be 0. Now, your book write it this way, but if you work it out, then you realize it's better to write it the other way, because right here, this just means u equals to small f, right? And if you write subtraction the other way, it saves, like I have here, for f, g, and h, it saves quite a bunch of negative signs. But anyway, so either way, we're going to do this. Now, if we go through this thing as we've been doing, then we have the Jacobian, right? And if you plug in the Jacobian and you get everything to work out, then you will come up with this. Now, please do this yourself, as I have done. Now, I have also got this thing to come out. Where is it? Okay, here's what I wrote. Okay, here is the problem. I wrote it like the way the book wrote it. And then I calculate, for example, focus on who's dependent on what, right? Right now we have, we're trying to plug it out such that our goal is such that xyz will become dependent on u(v)w. In that case, and the function f goes in that order. The reason we care about that is so that we know what f1 or f2 or g5 is, right? So this is the order of all the variables. And then we do here's the first method we might do this, and we do it like we've been doing in the past. Okay, use the old trick, which is we take partial derivatives of each equation, right? And then we use Cramer's rule and solve for things. And you end up, you see the way the book did it, we end up with a whole bunch of negative signs, which if we had reversed the subtraction, we would have been able to avoid most of those signs. But in any case, I worked with all the negative signs, or maybe pulled it out, I don't know. Anyway, I come up with this thing. And then as you notice, the book also avoided all the negative signs, okay? They just pretend that it isn't there. Well, not really pretending. They pulled it out, but they just don't mention it. Okay, and but anyway, so if you go through all this work like I did, then please do so. Okay, and I mean, I did it, so should you, right? And anyway, so you got here, and then eventually clean things up, and you will get what the book wants. Okay, specifying, of course, as always, the denominator, the Jacobian on the denominator is not 0. Then this equation will work out. let's see, do I have a negative sign in there? Let me check again. Yeah, see, never forget the negative sign. I forgot the negative sign again. And so, but once you've done that, everything is looking pretty good. Now, the second method is the new method we learned in this section, during which we're going to do some kind of Jacobian. Now, in order to do the Jacobian, then you have to calculate all kinds of stuff, right? Partial derivatives. And please do all this stuff, okay? Because f, g, and h is defined up here. And we have to do in this order. Where is it? Yeah, u, v, w, x, y, z. And then you need to calculate. So at this point, every variable is independent for big F, big G, big H. So we're just going to calculate it directly, okay, without worrying about, there's no chain rule happening here in this case. I mean, in this situation. So let's calculate all that stuff. Okay, and then and not make any mistake in any of them. And then the next page, where am I? Okay, right here. So continuing in the Jacobian calculations, then we write down what the Jacobian is properly. Okay, we're substituting, being that is partial y over by partial w, so we have x, y, z on this side. Those are the dependent variables. And then we'll put w where y is. See, it's w and y, right? So we'll replace w in the y spot for the Jacobian, and don't forget the negative sign. And then and once that's done, we'll plug all the stuff out. We plug everything in, and then eventually we'll solve for the Jacobian and come up with the same answer. It's important to do both. The reason, and I mean, all this looks like quite a bit of tedious work, but the thing is, this stuff can be quite confusing. So doing a reasonable amount of exercises will tune your brain into being familiar with it, and then it's no longer confused. All right, and so that's that. And next, let's look at example A, which we have on page 30. So example A, we have a simple little thing, right? And your book says, let's not bother with the Jacobian and just solve it like the way we always did, and not wear ourselves out, which is what your book did, right? It's a simple little problem, so we just solve it the simple little way we've always done, and very soon we'll crank out what partial u, partial y is, which is what we're searching for. However, I decided that we should still do the Jacobian, because that's what we're trying to learn here. So, so it makes sense to do so. Let me find it. So please do what the book did, but also do the Jacobian version of solving this problem. I feel that it's important that we go through these exercises enough so that you're comfortable with it. So we are going to follow the Jacobian rules, right? And then you write down what big F and big G is, which is the subtraction A equals to 0. And then remember who's dependent on what. Now, for now, I'm writing u in terms of like a function and a variable. It's just a lazy way of doing it. Later in the chapter, we're going to come up with a better way of saying this, okay? But for now, we'll just put out this. I just wrote this as a quick, easy way of saying what I want. So u is dependent on x, y. V is also dependent on x, y. And then so when we take partial u, partial y, we'll write down the Jacobian properly. As always, you put down y in place of u. See? Y in place of u in the Jacobians of the division. And then don't forget to make negative sign, plug everything in, and well, first calculate this stuff, right? Then plug it all into the equation, and then come up with something that is the same, okay? Which means it was correct. And so be sure to do example way in both ways, the old way and the Jacobian way. Now continuing, let's look at example B, where we have a similar story, okay? Various things, right? That we need to write it down equal to 0, then take the partial derivatives, and so on and so forth. And so, yeah, that's good enough. So please do this yourself. Just go through it like I did. So see, here is what I did, right? Doing example B, okay? We have F, E, and G, and then U and V are dependent on X and Y. and then we take the partial of equation 1 and equation 2 and come up with this stuff, and then slap on the Cramer's rule, and then eventually you got here, and that's where I stopped. Okay, I figure that's good enough. Okay, for example B, because it is quite tedious, and I didn't write out the answer, but that's sometimes considered good enough. So that is that bring us to, I think, the end of the section. That's right. Okay, so let's look at the homework. Now for homework, we are going to do, I'll find it first. For homework on page 31, please do problems, let's see, 1, 3, 5, 8, 9, 11, 12, 13, 14. Now, the circled problems are the ones with answers at the back. Well, not all the answers, some of the answers sometimes. The book tried to give us as few answers as he can get away with. Okay, so please go do your homework, and when you come back, I want to talk about them. All right, now that you're done with your homework, let's talk about it. Now, first, problem 1, we're just calculating the Jacobian, so I don't think there's much going on here. You just write down the Jacobian properly, okay? Which one are we doing? Is it with respect to U, V, and U, W, and V, and you have to write it down exactly as is, okay? So U is position 1, so I have F1, G1, etc. W is in position 3, so that you do the next row is F3, G3, etc. And finally, V is second position, so it's F2, G2, H2. So you just write it down exactly as is, and then you calculate the rest of the stuff out. And if you don't make a single mistake, which did I make a mistake here? I think so. I have a plus W missing, so I wasn't able to get the right answer completely. So I had to go back and check that I missed the plus W for some reason. Yeah, in this part, I think. But anyway, yeah. But we do have the answer at the back of the book for this one, so I was able to check it and find my mistake and get the right answer. So that's problem 1. Now problem 3, we are calculating some kind of a derivative. Okay, all right, so let's do that. We need to do it in 2 ways. First, the old way, which is we'll take the partial derivatives of these equations, okay, which we come up with 3 simultaneous equations, and then our goal is to hit dv by dx, right? So we apply Cramer's rule in the simultaneous equations and come up with this thing. This, I didn't write it this way, but this is the numerator and this is the denominator. And if you do the division, it will be correct. And the reason I know it's correct is because I did it the Jacobian way, and they come out to be the same, which I will show you right now. Okay, so here's the second half of problem number 3, where I did it by the Jacobian formula, which means you have to plug things in. Again, remember that to do dv by dx, you have to, here are all the dependent variables, and then you will put x in the position of v in the Jacobian. So I write down the same thing, except x is now in the position of v. Okay, slap on the negative sign, and that is your formula. And from this point on, you will write down calculate all these things, all 12 items, right? And plug it all in as you should. And in the right positions. And then you get this big pile of stuff, and that end up being this, which is identical to the one I did earlier. After you go through, I think I made some mistake here. Yeah, as you can see, I think I wrote down for G4, I made a mistake at G4 for some reason. I think I wrote an extra x in there, so I have a bunch of extra x's that I eventually figured out and had to scratch it out. And then my answer was correct, see? Yeah, I do tend to make mistakes a lot. But then there's so much stuff here, it's like sooner or later I'm stuck in a mistake. But by being very careful, then I can still catch them. Hopefully you're not like me and don't make so many mistakes. But if you are like me, then or if you when and if you make a mistake, just try to catch it, and then we're good, right? So next, let's look at problem 5, which we have our familiar rectangular polar coordinate conversion thing, where x is our cosine theta, our y equals r sine theta from I don't know, pre-calculus or something, when those the great days. So now we're going to work on this thing with the same trick. Okay, what are we doing? We're doing partial r, partial x, which we already know the answer to that. We've done this in basic calculus, but we're now gonna pull off the Jacobian trick. Okay, see how that works out. And so let's check so doing the Jacobian trick, which it means that r will be a function of x and y, and theta also a function of x and y, and we'll write down the big F and big G, and then slap on the Jacobian formula and calculate all the partial f, the f's and g's down here, and plug it all in properly. And eventually we realize that this thing equals to, what are we doing again? Partial r, partial x eventually equals to cosine theta. How interesting is that? Now, so that's what the Jacobian says. Now let's do things explicitly. That is the way we've always done. Okay, the explicit way, of course, is much faster. As you can see, r is the square root of x squared plus y squared, and then partial r, partial x eventually becomes x over r. And what is x over r? Is cosine theta. Why? Because x is defined as r cosine theta, right? So that's so then we know our calculations are correct. So that is problem 5. Now problem 8 is an exception problem. That is, it shows us sometimes when things don't work out. And here's an exception problem where you look at the problem and you notice that the problem looks very similar. Okay, the two equations, the first one is u squared, v squared, x squared, y squared. The second one looks almost identical. And with simultaneous equations, if your two equations are very similar, there are times that one equation might be too close to the other one, isn't providing enough information to solve for it, which is in this case is true. Okay, the second equation slap a log on there, and that doesn't actually help matters any, because when you calculate the determinant, that is the Jacobian. Okay, let's see. When we calculate the Jacobian, what do we see? Then we see that everything turns out to be exactly, got subtracted out completely. Okay, there isn't a thing left. The thing is identically equal to 0, which means the Jacobian formula does not work. So we're going to investigate this situation and figure out what is going on here. Now, so we're going to solve these two equations directly. At least try to see if we can. Now, to solve these two equations directly, I plugged something into something else. So this is equation 2, okay? And then I took equation 1 and slapped the log on it as well. So then we end up with something like a equals to what, if you let a equals to y squared minus x squared, then log of a equals to negative a. And then I solve for a. How did I solve for a? I plugged it into the decimals calculator, which gave me the answer of a, just this equation right here. Okay, I plugged it into the calculator to solve for x, replace a with x, and then figure out exactly when this equation crosses the x-axis. So that equals to 0.56 or whatever. And this equation, which when you plug it back into here, that is a hyperbola equals to a, and it looks something like this. Now that is the only time where these two simultaneous equations are going to make it. Now if that is the case, well, the hyperbola, the path of the hyperbola is not open. Okay, it's just two lines. There's no space there. We need space. So it is not an open domain. So there is no open domain for x and y such that these two, in this u, v, x, y, such that this thing works. Okay, so that's why the Jacobian collapsed. Anyway, so that is an interesting case that you can enjoy. I plotted, the hyperbola looks like this. I plotted it on the calculator, but I really don't see why you need to either. It just looks, it's a hyperbola, okay? And so that's that. So problem 9, we have we are supposed to use the Jacobian to calculate, I believe, partial u, partial x, and partial u, partial y. So that is straightforward. By now, we have done this enough times so that we write down stuff. Okay, be very careful. Always be careful as to what is the independent variable and what's the dependent variable. And once you remember that, write down the Jacobian for both cases, and then calculate all these f's and g's, plug it all in, right, and then make things come out, and it is correct. See, the book gave the answer for just one of them, and it turns out to be correct, and so hopefully that means the other one is correct as well. So that's problem 9. And problem 11, we have a shorter problem where there's an interesting situation. That is, let's say we calculate partial u, partial x, okay? And then the question is, so we did that, so and that happens to be a short problem, so we come up with a nice clean answer. And then we calculate partial x, partial u. And the question is, are they the same? And in this case, the answer is yes. Okay, once you get through it, you realize they are the same. So next, so problem 12, we're doing a similar thing. We are calculating first partial u, partial x, figuring out who is dependent, who is independent, okay? And then so that we can come up with it. So we got partial u, partial x, and then we get partial x, partial u, and notice that they are not the same. Okay, so the answer is no. They ask if these things are like are we supposed to talk about the same, or give me a second. Oh, in the previous problem, I forgot to mention that the question actually asked for reciprocal, right? That is, partial x, partial u is 1 over partial u, partial x. The answer was yes. Now, in this case, the answer is no, because it is not the reciprocal. Because when we do the math and get everything, look at the two formulas, they're distinctly different. So generally speaking, one is not the reciprocal of the other in this case. So it's not necessarily true that if you calculate one and want to know the other, all you have to do is slap on 1 over, and then it's all come out. It's not necessarily the same. And due to, well, things are that's because of various things it's dependent on and other reasons. Well, anyway, so when it is the same, it's more of a luck thing. There's no guarantees. So next, let's look at problem 13. So problem 13, now we're going to do the what is this, pre-calculus. So we're going to do some old problems, okay, where we are going to plug something out. That is, we're going to solve for something. Solve for what? U or V in terms of the other one explicitly. And what did I have? Okay, eventually I was able to calculate that V is this thing, right? U is that, after you pull it out. And of course, being that there's a square root situation, you have the plus and minus square root and stuff, and I didn't really bother, okay? So I just stuck with a positive one, and let's call it done. And you can, of course, to be perfect, you really should worry about the negative ones and stuff like that. Anyway, but in any case, we are able to figure out that in this situation we have what the book wants is that we have various numbers, okay, and then we have 2 sets of solutions for whatever it is they wanted for the implicit problem. And well, the purpose of doing that, why are we doing that? It's just to get a feel of what things are like, or remind ourselves what life is like when you try to find the inverse of something. So the next problem then, in problem 14, then we're going to actually do the Jacobian. This is based on problem 13. So we're going to calculate the Jacobian and then come up with something, which I did. Okay, and hopefully I didn't mess up here, and that is the right answer. But generally speaking, this is just another solid example of what the Jacobian does and how it feels to calculate this stuff. And that marks the end of this section.